Have you ever just, looked up at the stars and wanted to visit the most extreme, unreachable places in the universe, like the heart of a star or the core of some distant alien planet? Well, in this explainer, we're going to see how scientists are doing exactly that, and they're doing it without ever leaving a lab in France. It's pretty wild.
So, let's start with a really big question. How do you actually explore the heart of a planet? I mean, we live on this giant ball of rock and metal, but what's really going on thousands of kilometers right under our feet? How could you possibly get there to find out?
Well, the blunt answer is you can't. It's just physically impossible. The deepest hole we've ever managed to drill, the Kola's super deep borehole, only goes down about 12 kilometers. That's not even scratching the surface of our planet's 6,000-kilometer radius. The core? Yeah, that's completely out of reach.
Okay, so if you can't go to the mountain, you bring the mountain, or in this case, the planet's core, to you. Science has figured out an incredible way to recreate these cosmic conditions right here on Earth. Okay, let's dive into this.
You see, to understand the cosmos, everything from the chaos of an exploding star to the weird magnetic fields of an alien world, we don't always point our telescopes up. Sometimes we have to look down, into a laboratory, and literally build a tiny piece of that universe ourselves. So let me introduce you to our cosmic forge, LULI2000. It's located at the École Polytechnique near Paris, and this facility uses these mind-bogglingly powerful lasers to crush and heat tiny little targets, creating states of matter that otherwise only exist in the most violent and extreme places in the entire universe.
The research they do here is really built on three incredible pillars. First, understanding the actual physics of stars and galaxies. Second, decoding the secrets buried deep inside planets. And third, pioneering a path toward what is basically the holy grail of clean energy, nuclear fusion.
So how does a place like this stack up against other massive science projects? Well, the best way to think about LULI2000 is not as a tool of brute force, but as one of incredible precision. It's really less of a sledgehammer and more of a cosmic scalpel.
And this table really tells the story. You've got the American NIF, which is this colossal facility. We're talking the size of 3 football stadiums built for one singular goal: brute force fusion ignition. LULI2000 is, well, it's different. It's a precision instrument, it's open to academics from all over the world, and it's designed to ask those really fundamental questions about how our universe actually works. Think of it this way. It's where you perfect the experiment before you ever get a shot at running it on the big machine.
Okay, so how in the world do you use light to forge a star? The whole process is an absolute masterpiece of engineering. You're compressing an unbelievable amount of energy into a space smaller than a pinhead, for a time shorter than a billionth of a second.
That right there is probably the simplest way to get your head around it. The energy that the LULI2000 laser unleashes in a single nanosecond pulse is just immense, and it is all focused on one tiny, tiny point. And this sequence shows you the journey of that energy. It literally starts with electricity from the grid, which gets stored in these huge capacitor banks. Then, a single, really weak laser pulse is fired. It travels through a series of special neodymium glass slabs, and with each pass it gets amplified, just growing exponentially in power. Finally, a whole system of mirrors guides these now massive beams into a vacuum chamber, focusing them onto a tiny target. The outer layer of that target instantly vaporizes, creating this unbelievable inward shockwave that crushes the material to densities that are higher than the core of our own planet. Just wow! So, what's the point? All of that star-forging power is designed to unlock secrets we could never, ever discover otherwise. So what have we actually learned from all this? Let's go back to our original problem. We can't get to the Earth's core, right? We know it's mostly iron, but for decades, scientists argued about the exact conditions down there. LULI2000 gave them a way to find out for sure. So what they did was fire their laser at this minuscule sample of iron, crushing it with 3.3 million times the atmospheric pressure you feel at sea level. This allowed them to precisely measure the temperature at which it melts under those insane conditions. And the answer? About 6,000 degrees Celsius. And just to put that number in perspective for you, this experiment confirmed that the very center of our cool, rocky world is as hot as the surface of our sun. Let that sink in. We have a star right under our feet. But it doesn't stop with our own planet. Oh no. Experiments at LULI have also looked at common minerals, like magnesium oxide, under the even more intense pressures you'd find inside what we call super-Earths. And they found something amazing. This mineral, which is normally a solid insulator, transforms into a liquid metal.
Now this means those planets could generate a protective magnetic field in their mantle, not just their core. That dramatically changes our ideas about where we should be looking for habitable alien worlds.
This kind of fundamental research isn't just about understanding the cosmos for the sake of it. It's about building the blueprints for our own future. A future where we might be able to harness these cosmic forces to completely transform our world.
The next big frontier for these facilities is understanding this truly bizarre state of matter called warm, dense matter. The best way to think about it is like a super hot, super compressed fog that's not quite a solid, but it's not a gas like plasma either. It's something weird in between. And mastering this strange state, that is the key to unlocking technologies that sound like pure science fiction today.
You see, by mastering this exotic stuff in facilities like LULI, we could trigger a revolution. I'm talking about compact fusion power plants providing limitless clean energy, or laser accelerators small enough to fit in a hospital basement for pinpoint cancer therapy. Imagine creating materials that don't even exist in nature, like a room temperature superconductor that would eliminate energy loss, or even compact photonic rockets for deep space travel.
And this is really the grand implication of all of it. For all of human history, we have been a civilization powered by chemistry. Burning wood, coal, oil. This research marks a transition to something entirely new, a high-energy density civilization. A civilization where we don't just use matter, we shape it at its most fundamental level.
This knowledge gives us an almost unimaginable power. The power to literally recreate the building blocks of the universe right here in a lab. And that leaves us with a final, really profound question. If we can actually forge stars on Earth, what will we choose to build with that fire?